pictures, Slave. I don't understand. It's not letting me post a single damn thing.
So post it to the general, to the other chats, because it's too dangerous to for me to allow posting to the side
Okay.
chats. I'll give you mod powers. 1 second, Amber.
Okay, it's in general.
Roll. Okay, I made you
And she's
mod.
like surrounded by police. Thank you.
Chinas, I made you mod.
Are you into pegging, Mr. Slave?
Definitely. I'm into
Nice.
like anything that will inflict pain. Like I love pain. Pain is my
Your
friend.
volume dropped, Mr. Slave.
What? Anyway, let's get back to the ether theory. I'd rather talk about that than nonsense.
What, you don't wanna talk about pegging? You don't want to talk about how you like to get pegged?
No, I don't
Oh.
actually. It's actually boring. I want to talk about the ether theory, and if you have any questions about the ether, I'd love to answer. So,
Is Chinas your best bud in ether?
I mean, we used
Yeah.
to work together a lot, but lately he's been very busy at work.
Oh, I see. Nevertheless,
You can watch our streams.
did you guys ever do debates about the ether?
Me and Chinas? I mean, yeah. I
Did
mean,
you guys team
we
up?
we had this.
I mean, we debate with each other.
Yeah.
Is that true?
Mm-hmm. We've had our disagreements.
Impossible.
Wait, Chinas. So I asked you a question. You never gave me an answer about the video that
What
we
question?
watched. Uh,
What?
the video, the magnetic moment of the Stern-Gerlach.
What didn't I answer?
Let me copy.
Oh, I watched the video. Oh, right. Yeah, I watched the video, and yes, it's not that difficult to understand it if you want to go through it now.
Yeah. Forward to.
Okay, just wait a bit.
I want to forward it to the general chat. The general VC. Oh, there it is. Okay, found it. Okay, so it's. Where are we? Oh, I sent it to the wrong server. Oh my god. Let's try this again. Oh, General VC is the first one. Okay, so it's on the side. So specifically,
magnetic quantum
at 7:42, 7 minutes and 42 seconds. Or you can watch my stream. I have it open in my stream.
Okay, wait a bit.
Gamma, you're maybe you can put your mic to
Am
your.
I breathing into my mic again?
Yeah, put it to your side.
I am so sorry.
No, it's okay. Just so the trick is to never put the mic in front of your nose. Like put it next to your cheek.
Would have guessed. Yeah.
Here's the link to the stream so you can watch everything on the stream.
Numbers. In modern notation,
So, how do you explain the relationship between n and k and m? Why aren't they independent? Why is k up to n and why is m from negative to positive k? Why is that?
Okay, wait a bit. I'm moving stuff here. All right,
Oh,
I'm settled.
okay.
So your question is
Hmm.
okay. So wait.
Look at the stream.
Let me open your stream.
Yeah. Mm-hmm. Oh my god.
Wait,
Mm.
are you streaming?
I'm streaming, yeah. I hope.
You started streaming again 6 minutes ago. Okay, so
The-
MN,
the
so
link-
NM and K. Okay, so you understand why these are like integer numbers, right?
Yeah.
Okay, because
It's multiples.
this needs to be quantized in relation to
Yeah.
the Planck constant.
Yeah. Mm-hmm.
So okay, where is the diagram? Wait, I'll open the video.
Who did we lose?
Wait,
No, we
you got
gained.
Someone
obscure.
came in.
Let's obscure the.
Yeah, just
Hey!
nice.
Wait, what?
Oh,
What?
Obscure, what did you say?
Oh, I said it's just me.
Oh, you're the highlight of the show.
I am?
Hmm.
Why?
I don't know.
Your big brain.
Nah.
I don't know. I'm getting the vibe that you're like super hot.
Where did that come from?
I don't know. I don't know. Somebody said that.
Can't be
Your
hot
voice.
and also be smart as a woman. That's not a thing. So.
that's a
Nah,
dumb
that's
fucking thing for
definitely
you
a
to say.
thing.
Oh, it looks like I angered some ugly smart women. Or yeah. Sorry, guys.
Yeah,
You
I
wouldn't have
think
got
you
so
just
mad. What?
I think you just find fulfillment in like giving me an insult every time I join.
Perhaps. Yeah.
Yeah.
It's
Seems
I
to
do
be
it.
like a common pattern here.
Trying to what?
It seems like a common pattern here.
I mean, it's I think like it actually has a name when men diminish women in order to make them feel belittled. So that
It's called negging.
negging, yeah, negging, like causing negative self appreciation. So
Like pegging with my words.
exactly.
Yeah. Reminds me of Mr.
I think he's
Flynn.
mostly joking, right, Gamma?
What?
Like you don't actually mean the stuff you say.
That's up for you to decide, I guess.
Yeah, I'm just gonna say that you don't mean it.
I don't
Well-
disclose that information.
No, Gamma is actually a very nice person, but I think he's very
I don't
young.
know. He's
No,
uh-huh.
he's very young,
Oh.
and when it comes to women, he's still rough on the edges. I think.
It's just, yeah.
Okay,
Right.
listen. Sexism aside, dysgenic people are typically less attractive because that is how we are wired. Like intelligent people have better genes. We want to procreate with them. they survive better, which is the whole point of evolution. Like we are obviously attracted to mates that are physically more attractive, and physically attractive people tend to have better genes, which will make them smarter.
Well,
On average.
I'm physically attracted to Mr. Slave, and that's why it's so angering to me that he
How are
doesn't-
you physically attracted to a void? You've never seen him.
I just know he's attractive, right? He does MMA supposedly, right, Mr. Slave?
I haven't done it in a while because I have an
Well,
injury.
I'm sure you're still very good at it, of course.
Yeah, I mean, I'm amazing. I usually like mop the floor with everybody. Yeah.
Yeah.
Anyway, no, obscure. So I think, Gamma.
Nevertheless,
Yeah. Look, Gamma is really funny, and he always defends me. Like when we go to his Globes server where everyone hates me, Gamma protects me.
Mhm.
So Gamma has
Right.
he has built-in protective instincts. But I think that
Right.
my intuition is he's hearing your voice and he's turned on, and
whoa.
it destabilizes
Is
his
it just me or can I not hear him?
what?
Oh, repeat like the last two sentences.
So I'll repeat. I don't know where you didn't hear from. So, like when I go to the Globe server, I get harassed. Like you cannot believe. If you think that that you're harassed by him, you haven't been to the Globe server. What they do to me there is inhumane. It's like
Yeah,
I would
they
not
abuse
do that to an animal when I slaughter it. Anyway,
Yeah.
so Gamma is my defender, and he puts himself on the line. He throws himself on the fence when in order to defend me. So he's very protective. His protective instincts are very developed, very honed. But I think and with everybody else he seems to be fine. But when it comes to chicks, like Amber and you, I see that he becomes destabilized. He's no longer himself, and he's no longer protective. He is actually what's the opposite of protective? Offensive, maybe. Yeah, he's offensive,
I see.
but I think it's because I mean it's I mean give him time and
They're
cu-
funny, Mr.
maybe.
Slave.
I mean that's my psychoanalysis. Look, I have to be able to explain. I mean I see a phenomenon. I'm trying to explain it. So that's all.
Wait, Mr. Slave, you took out my channel status that I left. That's so
Because
sad.
we were under attack today. I did a lot of. I removed.
That's
Oh,
true. Yeah.
wait, obscure. Let me give
Oh.
you mod, so you can do whatever you want.
Oh.
Okay, there you go.
Okay, cool. Thank you.
So, but in general, Gamma, like if my record or my experience with women is that actually women appreciate it more when you're nicer. Paradoxically.
Yeah.
I'm not trying to get appreciation. Your psychoanalysis is off. I wanna revel in your love, Mr. Slave.
We've been through this. You said you're not gay.
I make exceptions for you.
I don't believe you.
Let's see, this that he's doing to Mr. Slave, you need to train to do it to women.
Wait,
That's the key.
Yeah. I'm training my domination skills for Mr. Slave
Yeah,
since he's into
but
that.
don't train with Mr. Slave.
Yeah,
yeah.
I can't, or else it'll
Guy
turn him
go
on.
on Discord and get into some servers that aren't toxic and they're sheep, and then you try to beat on them. That's it. That's the
anyway,
plan.
Chinas, what's the answer? Can you figure it out? You said you.
Okay, oh, yeah. Okay, so the N, K, and
Yeah. Why is K
so
up to
the
N?
M. Okay, so these are basically like quantum numbers for the electron, right? You understand that? So the M corresponds to the spin of the electron.
The N is the
So the
principal.
spin can only,
The N is the principal orbit. So it's like the
yeah, N
XY.
is the principal orbit. So
I
it's
would say
basically like
I would say it's the XY plane.
no, so N is like how close you are to the
Amber,
center
you killing
of
us.
the atom. Yeah, kind of. Uh,
I made
so it's
one
as close as
sound in like 4 hours.
No, you keep making a lot of noise. It's like all the time. Yeah, go ahead.
so N is as close as you are to the center, basically. Like it's the typical energy level of an electron.
Okay. It's the orbit.
That's the N. Okay, so K is basically like a number that is correspondent to what kind of shape the orbital will have.
What do you mean? Give me an example.
Okay, I can't send pictures anymore in the chat, so I'll send it to General.
Wait, you're
Okay.
mod. I gave you mod. You should be able to do whatever you want.
Oh, okay. I have mods. I did not know.
Yeah, I forgot to tell you.
Wait a minute. K has to do with the shapes, but I'm trying to get like a good image of electron shape.
What? Anyway, obscure. Are you there?
Yeah, what's up?
How was your? Did you do any work today? Did you study?
No, today was my break day. I baked cookies and then
Amber,
I made like a birthday card.
Amber.
Oh my
Dude,
god,
I'm
Mr.
not
Slave.
doing anything I don't normally do. Like,
Yeah, but now we're having like the the channel is growing. The server is growing. There's many people, and you're killing
now
it.
that we got attacked once, you think that you're like Destiny?
I'm Destiny. I'm literally Destiny. Soon you're not gonna see me on the Discord server. I'm just gonna let the mods, mod, and I'm gonna be only on YouTube. Yeah, that's coming up.
Yeah,
Sucks to be
Alan
you,
K.
because I'm already canonically part of the Destiny verse, because I had a whole fucking thing go down with it.
Oh, okay. They
You're
they
part of the Dennis universe.
they banned
There's an
me.
unfortunate story about that.
They banned me on my first day because I was uh streaming from the server, and apparently that's a violation. They told me
Yeah, I've been doing that for like fucking ever.
delete all the videos you recorded on our server or we'll ban you right now. So I said LOL, ban me.
That's awesome.
Yeah.
What idiots. What kind of an idiot, like, you give an idiot mod rights, mod privileges, and they just go Looney Tunes. Okay? Delete all your
I
videos.
mean,
The
these are
police of the
probably
Destiny verse.
these are these are probably instructions from Destiny. So
Wait, Chinas, I never understand what you're saying. I never understand
these
what
are probably instructions from Destiny.
No. Destiny
The
keeps
mods.
complaining how he's banned from Twitch. He doesn't stop whining, and he doesn't care that people are banned from his server. He doesn't understand that it's the same. That the way that he's banned from Twitch,
I mean, Destiny is kind of stupid. So
no, he's not.
Yeah, Destiny has like mental aids.
Mental
Isn't
aid.
Destiny
yeah,
a liberal?
yeah,
That's what
huge
mental
liberal.
aids is.
He's a
Stupid.
liberal. He's a liberal, but he's not as bad as a lot of liberals. I mean,
No, it just had a relationship with a girl who had a relationship with another guy, and he
no,
was saying that yeah,
no,
that
no. He
that was
he
perfectly
had
normal.
many
That's how
streams.
much of a liberal he is.
He had many streams. He went into the details. That was not the issue.
I'm losing you, Mr. Slave.
You're losing me? How?
Your volume is going down.
Oh, maybe because I'm cleaning my nose. I'm sorry. I had to move the
Okay.
mic up. Yeah, I need always my nose to be clean. It's always so. I always clean my nose. Anyway, go ahead.
Okay, so you see this image, right?
Yeah,
L and K, yeah, it's the same.
yeah.
L and K is the same. This is basically like
What do you mean L and
how
K is the
how
same?
the
Oh yeah, L and K is
yeah.
the same. Yeah.
Sometimes they use L, sometimes they use K for the same thing. So this is the number that defines the shape of the orbital, right? So there are like certain modes of the orbital that are stable, and yeah, that's it.
That doesn't really help much.
Okay, I mean, I'm just telling you what the dinks are. Like, you can now have an interpretation of how they come to be like this.
No. Look, he says I'm going back. This is Schrodinger. So we're talking now before Schrodinger.
Yeah.
So I'm talking about
Okay, but it was still, it's before Schrödinger, but it's also important to say that it's after the discovery of the quantization of of light and energy.
explain to me look. So I actually read Sommerfeld. At least the paragraph they showed during the video, he showed a quote from Sommerfeld, and I read. It's actually in German, and I was able to understand it. So Sommerfeld,
Okay.
I think it was in German. Wait, Sommerfeld? I don't know if it was in German. Maybe.
Yeah, Sommerfeld's probably German.
Anyway, I remember reading it,
But
and
they used to write in German anyways back then.
yeah,
Yeah.
okay. So when you read what he says, so basically, so Bohr came up with n. Sommerfeld said it's not just
Yeah.
n. N, I mean, Bohr was thinking Keplerian orbital planetary mechanics in 2D, that all the planets are in a single plane in XY. Sommerfeld said no. First of all, he came up with the ellipses. He said the orbits don't have to be circles. There's no reason. They can easily be ellipses, and like planets, it gives you actually extra stability. That's the first thing. Second thing, he said that we need to take into account Einstein's special relativity. So he plugged that in. So fine, I agree with that. And then he said, let's move from 2 dimensions to 3 dimensions and let's go to spherical coordinates. And the L, the L or K, and the other one, what was the other one?
K was replaced by L equals
So yeah, K and M. He said,
Okay,
well,
and
M is basically
N, K, and M. L is the same
M
as
is supposed
K.
to be
So
phi, and K is supposed to be theta, and N is supposed to be the radius. So it's radius, phi, theta. When you read Sommerfeld's paper, where he literally introduces N, K, and M for the first time, that's how he does it. He first.
okay, but look at this last image when they combine the other ones.
Whose last image? Your last image?
Yeah, last image I sent.
Okay, I mean that's already Schrodinger, and
No, but this is N, K, and M. The
but
first
why?
column is N. It's just
But
just
why?
just very N.
Listen.
The
I'm
second
asking.
you
Hold on.
you start the you start the
Hold.
okay.
Wait.
Sure.
So my question is, let me go get the image that I sent you, so I have it available. Did I show you the image? Yeah. How do you copy the image? Oh, okay. Copy image. All right. Now let's bring it here. Let's upload it. Okay. So this image. Explain to me why K is only up to N. That's my only question. Why isn't K
Okay.
independent? Why is K limited to N?
I mean, if you look at the images, you kind of get it.
Look at the images. You
But
mean the next image in the video?
no, the image I sent you.
But I'm looking at Sommerfeld and I'm looking. Who left? Oh, what's her name? Amber left. Why did she leave? So what's the answer? So what images? You mean the image from the video?
And magnetic quantum
No,
numbers.
the image I sent kind of gives
But
you
the image, I'm
some
not talking
idea.
about the image that you sent. I'm talking about the video that I sent from Dr.
Yeah,
JK0. From JK0.
but but what I'm trying to tell you is that you can get some idea of that if you look at the picture that I sent you.
What do you mean some idea? I'm familiar with the Schrodinger orbitals. How does that help?
Yeah,
How does that help?
it's like you can divide. Like you see, for example, the first line in relation to the second line. Like you get different modes as you get more orbitals.
I don't
But
understand.
I honestly, I mean, I would have to study this better to really explain to you why physically this can't be. This needs to be like this. But you can sort of see
See what?
that
Wait, hold
when
on.
you
Obscure, Obscure is a chemist. Obscure, can you explain this, the Schrodinger orbital?
I think you're just giving me labels, Mr. Slave.
What
What
do
am I explaining?
you see the last image that China sent in the side chat?
Yeah.
Can
Oh,
you?
the LM and the orbitals.
Yes. Can you explain that?
The way I was taught is. Wait, I can explain it. Give me 1 second. Okay, let me pull up my notes from like last year.
Okay.
You mean like you want to know how to count it? Like you want to know what the value of, know how to find the value of N, K, and M?
I mean, if China's claims that that this has some relationship to the Stern-Gerlach experiment, which is what the
I
video
mean,
says.
that's not me claiming.
Yes,
That's the
yes.
video
Yeah,
that's
the video claims
talking
that
about
this
that.
is where it starts, like where it comes from. So I'm just trying to understand. Okay, where does it come from, and where is it going? What is the
Oh,
significance? What is the
all
relationship? Hmm.
sorry, I didn't mean to cut you off. All I know is that N is like the electron's energy level.
Okay.
M is the um orientation of like the what way the orbit is in space, and then K is just like angular momentum.
Let me see if that matches. So what he says in the video that we're watching is n is the principal. It's the length of the radius, which I guess is the
Yeah, that's the principal quantum number.
okay, and then k is
Yeah,
the
and
azimuthal, which means some angle. I don't know. And m is supposed to be
yeah,
magnetic.
K is supposed to be like the orientation, the absolute orientation on one axis, right? And M is supposed to be like some kind of wait, M is supposed to be some kind of deviation from that. Let me check.
So I'm looking at the image that you
Okay, M is
posted.
a magnetic moment. Okay.
Like Obscure. If I told you three numbers, the N, L, and M, would you be able to figure out the shape? Is there a logic in the shape? Can you think?
Yeah, not now. I'm trying to understand exactly how to do that. But the way I see, for example, in the equation that he makes afterwards, like,
Okay, I mean,
okay,
okay, look, like the first number, the principle, the energy, the radius, so it just grows. So when you go from 2 to 3 to 4 to 5, it just grows, which I can relate to. So 2 to 3 to 4 to 5, like the shape is not supposed to change. It's supposed to grow, but then the shape starts changing. 2, 3, 4, 1, 1, 1, 1, 1, 1. Yeah, the 3, 2, 0, 3, 4, 4. This is so confusing. 3, 3, 3, 3, 3, 3. This is R equals 3. As far as I understand, you plug it into Schrodinger. You plug these numbers into Schrodinger as some conditions, and based on that, Schrodinger gives you these shapes. These are supposed to be standing waves. Oh, obscure left.
so
Yes. Yeah. What did happen?
Wait, Gamma, do you know this stuff?
this is interesting because,
No.
like,
No. I do not.
Hey, obscure. what
Sorry,
happened?
can you
because,
hear me
like,
now?
Yeah.
Mr. Slate, repeat your question. If you give me 3 numbers, what happens?
Oh, if I gave you three numbers, can you figure out the shape? Is there a logic to the shape from the numbers?
Yeah, so like if L is equal to 1, then you know it's like a p orbital.
And
And if you like, if you know the n, right? So if n is 3, then you know that it's in the 3rd energy level. And then if you know the magnetic, wait, what was the other one?
well, there's N, L, and M. M is the magnetic, supposedly.
Yeah, L like will like help you know what the range is of the M. So you know it's between positive or -1 to +1.
What does that mean?
What I like the way I memorized it, I just know how to do it in problems. I don't know like the actual theoretical way of doing it. I only know like you mean what does what mean? The P level, the
Okay, let's
magnetic.
look at the diagram. Let's start from 2, 0, 0. That's the simplest, right?
Okay.
So N,
okay, I see.
so N equals 2.
I see 0.
And then you go to 2, 1, 0. You move 1 to the right. 2, 1, 0. So the 1 is L equals 1. L equals 1 is the p orbital, which is the two, I guess it's the two balloons on top of each other.
Yeah. Yeah.
Okay. But
And
then,
then you have the
oh, but
3 is the d orbital, right?
and then I go to 2, 1, 1, which is the same as 2, 1, 0, but now the M is equal to 1. Oh, so M equals 1, you just rotate it. So you can also have -1. Oh, I see. Okay.
Oh, I see the logic of this now. Yeah, I'm seeing the logic of this now. Like you see the 2, 0, 0, it rotates. Imagine like y is pointing towards you, like, and it rotates around y, and the other one is rotating. The other one is like the 2, 1, 0
Wait, I don't know what
is
you mean the other one. Like, talk, tell,
oh,
I
in
mean,
the image.
yeah, but use the
So you got the
numbers.
2, 0, 0.
Okay.
Huh?
Yeah, use the numbers. Yeah.
You got the first one in the image that I
Use the
sent.
numbers. Use the numbers.
Okay, so n equals to 2, the other is equal to 0.
Use the numbers. So you're talking about 200 and 210?
Yeah, the
Wait,
difference between those two.
Yes, obscure.
What's the problem? Like, I don't get what you're confused about.
Oh, it wants like a logical framework to figure out what
Where
the
did these
orbital should
numbers
be.
come from?
What the two? Okay, so 210, right? Let's take 210. 2 is your
Oh, we know
energy
that.
level, so it's in the second
The question,
energy shell.
the question is, where did these shapes come from? Who decided these shapes?
The types of orbital shape?
I guess.
Like, why? I have no idea. We didn't learn that. All I know is like one that if it's a circle, then it's a S.
Yeah,
If it's like a
S is
infinite symbol, it's a P. If it's like a flower, it's D.
yeah, that's advanced quantum mechanics, like the Y parts.
yeah. We're doing
That's like
the
master's
actual.
degree type of stuff for doctorate.
We're doing right now
Yeah,
like where it actually comes from. Like how do we know
Yeah,
this?
you don't learn that in normal chemistry.
yeah. So I don't know anything past like what you learn in university.
But basically, like this is like rotation around different axes. You can just
So the
think about that like that.
magnetic means you rotate, but how can you have so many?
Yeah.
But-
No, more or less. Like no, the angular one is the K or L. That's
Hmm?
the angular one. The magnetic is like it's another. It's just the orientation of the magnetic field,
I don't understand.
which also causes a different orientation on the rotation on
No,
the angular rotation. So yeah,
I don't
still
understand.
kind of works like that.
I don't understand. Anyway, I'm still as confused as I was in the beginning of the conversation. So
Okay, but see the images. See the first image, 200,
yeah,
right?
yeah.
That imagine the y-axis is pointing at you.
What?
That's the rotation.
What? I don't understand you. What?
Imagine the y-axis is pointing at you.
Okay.
That's a rotation around the y-axis, right?
What do you mean? What is the rotation
It's
around the y-axis?
the electron is rotating around the y-axis.
Oh, it's orbiting? You're saying the angular
Yeah,
momentum is
orbiting
pointing at
around the
me.
y-axis. Yes,
Oh,
orbiting.
you mean the M?
Okay.
This is the L?
Huh?
The M? The magnetic moment?
That's yes. That's
That's
the n equals to 2,
no.
L or K equals
There's
to
no
0,
M.
and M equals to 0.
Okay, in all of these N, the principal equals 2. So they're all supposed to be spherical.
Uh, no, that's not. It's not exactly spherical.
The N, okay, so
Because these
N
are also
doesn't,
like
okay,
the probabilities of
okay,
where you find
all right. So let's
the
assume,
electron.
so what does N tell you? Like I'm trying to understand what N, what the principle tells you.
Oh, n is easy. N is like it's like the energy level that you're at.
Okay, so that's the same as the length of the radius. That's the R.
Okay, yeah, basically that.
That's okay, so that's what Sommerfeld said. So N is R. So R grows by multiples of H, and that's the first number. Okay. The second number is the L. Let's call it L. So when we are in
Okay,
the
so
two
that's
energy
what I'm
level.
trying to explain. I'm trying to explain the L and the M. So the L,
Mm-hmm.
for example, you see that 200, it goes around the y-axis. Then
Okay.
if you go to 210,
Yeah.
you're not going around the y-axis. You're going around the x-axis. You understand?
But let me ask you this. 200, is it the two balloons or is it one, is it a sphere? 200, is it a sphere?
Yeah, it's a sphere, but like I don't think I think that's a specific, like the rotation of the sphere is like a specific orientation. I think so. That's the thing. Yeah, that's a sphere, and the rotation is a specific orientation.
Okay, I don't know what's going on.
I mean, I'm not
How is 211?
Centaur is not really a sphere. It's more like a toroid, you know? It's rotating around that.
We need a This is no good. This is a terrible GIF. We
Yeah,
need a
but I
three.
can see the 3 dimensions
Yeah, we
from
need a
here.
three-dimensional image. This
Okay,
is
oh,
useless. But I'm not understanding. Oh, Gamma, you're.
I got some images.
That's amazing.
Huh?
That's amazing.
Okay, I got this.
I don't know how to play Kerbal.
Oh, this is RSS, so it's even harder.
Oh, wow.
Yeah, real scale solar system. So
Is it Earth or is it a different planet?
yep, it's Earth, and I just accidentally pressed space, but that's fine.
Wow, amazing.
This is just
Genus-
for engine
Okay.
reuse.
Engineerius? What?
No, engine reuse. So I'm reusing the engines.
Oh, I see.
Yeah, all the expensive parts instead of reusing the whole booster.
Yeah, that's the plan. Atlas is going
Okay,
to
so
use
the
it.
first one is a sphere. The other one is like 2 spheres. So you got 2 orbitals, and they divide themselves into spheres.
So S
the
there's
first one is 2 spheres,
so
1
S.
level.
1 second, listen,
Okay.
Chinas, 1 second. So S could grow, right? You could have more, like bigger energy. Like obviously, you could go into higher energy levels.
Yeah, it's like you could have various shells, you know.
So it would be 100, 200, 300. These are all S? No. Or yes.
Yeah.
So you can
Wait,
grow.
yes, those are all S.
Okay.
So
And then P.
the one is like.
But what are the
Yeah,
numbers? What are the numbers for P? Tell me the 3 numbers.
P is L is 1, so the L would be 1.
But
So
what is N?
N is the first one. So like first number you see is N. The second number you see is L, and the third number you see is
I
N.
mean, first number is L equals to 0.
Yeah.
And yeah, that's the S. And the P's are L equals to 1.
And then D is
the
L
P
is 2.
L is 2. So
Mm.
then we need to make a distinction of M as well. Because
So L determines the shape.
Yeah, L determines the shape. But
Yeah.
M also does something here. Because M seems to determine the orientation. Yeah.
But how is the orientation? Like, why should we care about the orientation? I mean,
Yeah,
because
it's interesting. Like, what is even like this? This has to be like the orientation has to be like a representation of the orientation in relation to something. So it should be like the orientation of the magnetic momentum in relation to the rest. Yeah.
right. So I think
Should be,
if you
has
can
to be
think
that.
of it, you can think of it like in the Stern-Gerlach that there is a magnet. There's a magnetic field. And in a magnetic
Yeah, it's
field, it
basically
can only 1 second, 1 second. In a magnetic field, it can only switch to these 3 directions relative to the magnetic field.
yeah, more or less. You have to interpret what he says next in the video to understand that.
Wait, Obscure, do you know anything about the orientation? What number? That's the
Yeah.
magnetic. So I guess that's the magnetic. The M. The M is the orientation. Is where it's pointing.
Wait, repeat what you said.
the M. Like I'm looking at the p orbital. P,
Yeah, M is where it's pointing. So if M is 0, then so it basically describes the orientation along whatever the orbit is, like whatever axis that you want to look at it.
but relative to what? Like relative to what?
Relative to the axis.
No, but there are no axes in reality, right? What is it? When you look?
Yeah,
I mean,
but in
one
this
second,
case, it's got to be the
Chinas, let me finish, please. One second.
sorry.
So at the end of the day, you look at a molecule, right? You're gonna look at a molecule, and it's gonna have a shape, and that molecule can point any which way. It's not limited. It could be spinning. It could be bouncing. So how can you tell the difference between a molecule that is P0 compared to P-1 or P1? Like these three molecules should look identical. They look identical. They're just pointing in different directions. But what does it mean to point at different directions? It's not like the universe has a direction. There's no XYZ in the universe.
Right. Oh, yeah, I know why. It's because when p orbitals have different like orientations and you have which correspond to the different like m levels, right? You remember how like do you remember learning about shapes and hybridization in chemistry? So because you have p and then the m, it helps explain for example, like a boron is trigonal planar. Why is it trigonal planar? Because of like the specific arrangement for that molecule. Or like methane is like tetrahedral, right? It's tetrahedral because the p orbital is this way and then the m orbital is, or m is this way. That's why. Especially like even with water.
No, I didn't.
That's you use the m to predict the behavior of like the atoms.
But how is it? How is P0 different than P1? It's the same molecule. It's the same. It's the same electron. The electron is just pointing in different directions, but it's everything else is the same. So, how could you tell the difference? Let me ask you this: Can an electron point be configured in any other way other than P1, P0, and P-1? What about between P1 and P0? Isn't there like a halfway through? Like what's stopping it from being configured halfway through? I mean, it could be spinning, right? The whole atom could be spinning in space. Why would it care?
That's a good question. I don't know.
I know. Because it's in relation to a magnetic field.
Mm-hmm. Okay.
Everyone's silent.
Yeah, I'm okay. Yeah, I mean that's basically the whole Stern-Gerlach and the whole spin and Sommerfeld. That's basically it.
Kind of circular.
I don't know if it's circular, but there's
circular reasoning.
I don't see how that. No, but so when you try to reconfigure an electron shell, you can only do it in multiples of h. And h is an angular momentum, so you cannot change it by less than.
Yeah, but that's the part that the video explains afterwards, right?
How? Okay.
By the way, Amber is gone. I didn't even notice.
Yeah, she left. I don't know why. Let me check.
Okay, so you watch the next part of the video, and then he explains why M is also quantized. Are you watching?
No, I'm checking up on Amber. 1 second. Okay. Okay, so what we're saying is that the magnetic moment is in multiples. Okay, what about the orbitals? Okay, who determined that S is going to be a sphere, and I guess S is energy level 1 and P is energy level 2? No. The shapes is the L, it's not the N, it's not the principle. The principle is just the energy. So anything can grow, I guess. If you add more energy, the same shape grows. Is that correct?
More.
Doctor,
Yeah, that's adding n.
Dr. Obscure?
Oh, sorry, what? I was not paying attention. I was doing something else.
So, like, if you look at the image, the last image that China's posted in the side chat, that's what I'm looking at. So,
Yeah.
so we're looking. The first one is the sphere, the red one, the S orbital. So that's would you say that's 100?
Um. Yeah. Right. Let me see.
But is it also 200 and 300 and 4 and 5 and so on? They all look the same, right? But I see that 200 is 2 spheres, 300 is 3 spheres, 4 is 4 spheres, 5 is 5 spheres. So an electron is simultaneously in 5 spheres.
No.
Isn't it?
Wait,
This
that's
has
a
been
good question.
so.
That's what it
Does
looks
it
like.
have to be one electron?
No, but it's a standing wave. It could do whatever it wants. I mean, like we have constraints. Look, we have the Schrodinger wave equation. We're applying all these magnetic and energy constraints, and it's forming whatever shape the mathematics forms. We're right.
It would be the same. Oh, sorry, I didn't do that.
Yeah, go ahead.
Okay, so based on my understanding, I could be completely wrong. Based on my understanding of it, the first number, if it's 100, it's just wherever the energy level is, right? So it would all be the same shape because the shape isn't moderated by the n.
I mean,
we don't care about the shape when it comes to the first, because the first one just tells you the energy level, right?
but it's a sphere. No?
Right. So it's always going to be a sphere.
Sure. Okay.
Yeah, I mean, a sphere just means it's the same probability everywhere around.
I
that
don't
level.
buy the story with the probability. For me, it's a standing wave or
Okay,
it's a wave. It's fine. No, it's not nothing to do with probability. I mean, obviously,
But you
obviously, if
can have standing
obviously,
waves, they call it.
obviously, if it's a standing wave or it's a wave, then it's also the probability. Like, where are you going to find? But I don't believe there is a particle. I believe it's always a wave. So I forget about. I'm going to ignore the probability. Let's just look at these
Okay.
shapes. All right, Obscure, go on.
Go on with what? Sorry, I was done.
So 100 is a simple sphere. 200, the electron takes up the shape of a sphere within a sphere, right?
Sure, yeah, because it's in the second energy level. Then
And 3 is 3 spheres, one inside the other.
3 is just, it's in the third energy level.
Yeah, but what does it look like? I mean, what's the shape?
I don't know.
I mean, we can run the equation. I mean, we have Schrodinger's
Yeah,
equation.
but you really have to see it in probabilities in this
It
case.
doesn't matter. I'm just looking for the shape. I don't care if you interpret it as probability or electron density. I don't care. I'm just looking what
You
shape does.
interpret it as having 3 ripples versus having 1 ripple or 2 ripples. You could also do that.
Fine. Anyway, let's assume
Yeah.
200 is 2 spheres, 2 concentric spheres. 3 is 3 concentric spheres. Okay. What is 110? Is there a 110? Probably
110.
no, probably not.
No.
Because L is supposed to be smaller than N. It's
Yeah.
N. L is from 1 to N minus 1. From 0, sorry. From 0 to N minus 1. N is 1. N minus 1 is 0. It's from 0 to 0. So there's only one L option. So in the first principal orbit, there's only one K, and probably the same goes for M. Negative L to positive L, but there's only one. It's both 0, so fine. All right. Oh my God. Let's go.
I mean, you could even see these as various types of waves, right?
What?
You could even see these as various types of waves.
I don't know. Right now I'm still not understanding where
You could see
some.
these as various types of waves.
Yeah, I understood what you said, which is an
Oh,
exception
okay.
to the rule, but I understood what you said. I'm just saying I still don't understand where Sommerfeld is getting these numbers, these relationships from. He says n is a multiple from 1 to infinity. L is from 0 to n minus 1. Okay, why? Why is
I
that?
mean,
So
I think Sommerfeld was looking into he was looking into like fringes of
what? What
that
fringes?
you get
What fringes?
on
What do you mean?
like, yeah, like the like when spectral lines, when you see an element, producing
Yeah,
certain spectral lines when
I don't think
hit by light.
I saw the video. They didn't mention spectral lines with respect to the.
But I think that's what he was examining and coming up with a model for.
No, no, I told you. It's after he said, let's go to 3 dimensions. So Bohr said, let's think like Keplerian planetary motion, XY flat. All the orbits are in one flat plane. Sommerfeld said, let's make them elliptical. Let's add Einstein's special relativity. And then he said, let's go into the Z direction. Nothing stops us. And let's go.
Okay, I see.
And then he switched to spherical coordinates. So he said R, theta, phi. And R is the principle, which is the energy. And theta is one angle and phi is the other angle. But then he has these relationships that I don't understand. I don't know. I just don't know. And no, and he's not
Okay,
explaining.
I mean, if you want to think about orbitals, you can also think about orbitals like making those
What do you
shapes.
mean? What do you mean if I want to think? I don't want to. I didn't ask for this. I mean, I'm fine when. No, when Sommerfeld, I understood everything. You can hear how I'm easily repeating everything Sommerfeld said up until the point of going into 3D. Once he went into 3D, R theta phi, that's easy. But then he came up with NKM or NLM with that's
Okay,
all,
so think about
which is also which is also fine. But then he came up with the relationship that K is limited, or K or L, whatever, is limited from 1 to the principal, and M is limited from negative K to positive K or whatever, or negative L to positive L. Where did these relationships come from? And then, the next slide, I also don't understand. But this is where I stopped understanding. And you're not, I don't think do you understand why he came up with it?
I mean, I don't understand it fully, no.
What fully? Do
That's
you understand?
definitely.
Yes or no? Fully schmully. You
I
either
mean,
understand.
I have some hypotheses for how we could be coming up with this, but I don't know exactly how we came up with this.
Okay.
I'd have to study that. I don't know. Ask ChatGPT. Let me ask ChatGPT.
Go ahead. Anyway, obscure.
Yeah, what's up?
So yeah, I'm trying to figure out the beginning of this orbital idea, where the Sommerfeld is the first one, I think, basically to come up with these three numbers.
Yeah, Mr. Slave, you asked really great questions about it. I just like learned it and moved on. Like this was last year. This was like a week where we learned this, and then I forgot about it till today.
I know. I remember when we studied this in class. I remember it made sense and we moved on. I remember. And when the teacher says it, it makes perfect sense. Like, okay, all right, makes sense, I guess. These are the shapes. The shapes can be derived from an equation, and it's incredible that it actually has predictive powers towards physical chemistry, that you're able to predict angles, actual angles of shapes of complex molecules. It's mind boggling because the equation is based on, it's a simple wave equation. It's the same equation that governs the oscillation of a pendulum. It's mind boggling that that same equation is able to predict so well the shape of an atom. That's like you would never think it up. Like what?
Yeah.
Okay, so what ChatGPT is saying is that what Sommerfeld did was quantized action. So in essence, he was minimizing action, but he was also quantizing it.
Mm-hmm.
So he did some Lagranges, probably.
Mm-hmm. Yeah, I remember now. Yeah. So it comes out of the
So
act.
we allowed for elliptical orbits, and then basically quantized and minimized their action. So that's what I'm understanding here.
Okay. Amber is okay. Everything is fine. Her husband came home. Okay. So you're saying it's the action. Okay. Then, so you're saying from the action, he got these constraints for the K and the M. So K and M came out of the action. Like, I guess N, K, I mean, N, I guess he fed in, but K and M came out of the action. I wish we could see his well, we could probably read his paper and see how he used action.
Yeah, might as well.
Might as well.
Mr. Slave.
What?
Oh, I was just gonna say bye.
Oh,
Bye.
thank you, Obscure. Thank you for joining us. You're the best.
Of course. Bye, Mr. Slave. I hope you have the best
Thank you.
night, day.
Thank you. See you
Yeah.
tomorrow.
You too. Bye.
Bye bye. Chinas.
Chinas, yeah.
Yes.
Bye bye.
Bye bye.
Bye.
La 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 la. Anyway, so okay, let's assume that he used used the action, whatever. But then the video goes on, and he says,
and magnetic quantum numbers.
Let's see
In modern
this.
notation, K was replaced by L equals K minus 1. Sommerfeld considered the atom in the presence of an external magnetic field, which defines a preferred direction in the space of the experiment. Without loss of generality, we can choose our coordinate system so that the z-axis points along the magnetic field. Although the angular momentum of
I'm watching the video from Dr. JK.
the electron points in some direction in space, Sommerfeld argued that any measurement of the angular momentum corresponds to a projection of the angular momentum along the axis defined by the magnetic field. Therefore, according to Sommerfeld, the angular momentum quantization implies Lz equals mh bar. If we call alpha...
Okay, so he says Lz equals mh bar in the z direction. So because the magnetic field is in the z direction, then Lz, the angular momentum, is a multiple of h in the z direction. But it can't be less than h. So as long as what does that mean? I mean, it's pointing in any direction. Do you understand what he's saying?
I'm not listening.
Can you look at my stream on YouTube?
I will. Okay. Where is your stream?
I put a link. Let me put another link.
Okay, for some reason your stream is not
Here it is.
loading.
Okay, it's called chilling.
That's stuck.
It's called chilling.
Okay, so I'm on your stream, but I'm seeing Discord.
Yeah. Sorry, my mistake. Okay, I'll do it again.
Okay, so I'm on your stream, but I'm seeing Discord.
Yeah. Sorry, my mistake. Okay, I'll do it again. You should
Okay, so
be.
I'm on your stream, but I'm seeing.
Yeah. Okay, you're looking at my stream, and I'm gonna look at his video on my stream.
So I'm on your stream, but I'm seeing.
Yeah. Okay, you're looking at my stream, and wrong again. Okay, here it is.
And magnetic quantum numbers. In modern notation, K was replaced by L equals K minus 1. Sommerfeld considered the atom in the presence...
Okay, you're following now?
Yeah.
Okay.
Of an external magnetic field, which defines a preferred direction in the space of the experiment. Without loss of generality, we can choose our coordinate system so that the z-axis
what do you
point...
want to know about that?
What?
What do you want to know about that?
Well, not yet. Let me get to the question.
Along the magnetic field. Although the angular momentum of the electron points in some direction in space, Sommerfeld argued that any measurement of the angular momentum corresponds to a projection of the angular momentum along the axis defined by the magnetic field. Therefore, according to Sommerfeld, the angular momentum quantization implies Lz equals mh bar.
Okay. Lz equals mh bar. Let me play that again. So any what?
We can choose our coordinate system so that the z-axis points along the magnetic field. Although the angular momentum of the electron points in some direction in space, Sommerfeld argued that any measurement of the angular momentum...
So he argued any measurement of the angular momentum
corresponds to a projection of the angular momentum.
Corresponds to a projection of the angular momentum
along the axis defined.
Along the axis defined
by the magnetic field. Therefore,
by the magnetic field.
According to Sommerfeld, the angular momentum quantization implies Lz equals m.
The quantum quantization implies that any measurement we do in the z direction will be a multiple of h.
Okay, yeah.
Now we know why. We know it's because everything is a multiple of h. You cannot have less than, like, photons are never.
No, but understand one thing. Understand one thing first. Is like the main thing here is that you have to consider that the only measurable L's you can never measure L. You can only measure LZ.
Yeah,
so
that's fine.
You're always measuring a projection.
Yes. Yes, and that projection must be a multiple of h. It could be. Could it be 0? I guess I don't see why not. Can m be 0? M is the same m. M is the third number. This is the M from the previous slide, I guess.
Yeah, it can be 0.
Could it be -1?
I think so. I think M can be -1. Yeah, M can be negative. There's no reason for M not to be negative.
All right.
H bar. If we call alpha the angle between the angular momentum vector and the z-axis, we can write the projection of the angular momentum as Lz equals the magnitude of the angular momentum times cosine of alpha. Then the cosine of the angle becomes this expression. From simple geometry.
Okay, this is still simple. Cosine alpha is equal to Lz dot z over L, meaning so Lz over L magnitude is the direction of L dot the direction of Z. So Lz dot Z, I don't get that. Lz dot Z? Lz dot Z is Lz.
Yeah. Yeah, it's just LZ. I don't know why it does that.
Because you lose the vector. When you do Lz dot Z, when you multiply two vectors, that's already a scalar. Dot
Oh,
product
okay,
is
so
a
that's why it does
scalar.
that.
So that's how you lose the vector. So now Lz, and then it's Lz over the magnitude of L. Right? Lz over the magnitude of L itself. So that's the cosine alpha. Cosine alpha isn't that the opposite? Okay, yeah, it's hypotenuse over base. Is it? Cosine is hypotenuse over base? Okay.
No, it's base over hypotenuse.
Then it's reverse. Lz,
Yeah, the thing that's the image is stupid. The image should be a 90 degrees angle.
he got the 90 degrees wrong. The 90
Yeah,
degrees,
he got the angle wrong.
yeah, Lz is 90 degrees to
Oh
Z.
god. Yeah, is 90. I mean, LZ is 90 degrees to well to no wait. No, the angle between the LZ
Wait,
and
if you're projecting
the line that goes to L is 90 degrees.
if you're projecting L to Z and that's Lz, then Lz must be smaller. The way he drew it, it looks like it's the hypotenuse. It looks like it's
He
bigger.
drew it in a very stupid way. But
He drew
the
it.
projection, first of all, shouldn't be on the zero. The projection should be in y equals to the same y as LZ. That's where the projection should be.
Well, it's supposed to be.
It drew it all wrong.
It's
not
supposed.
drawing a projection right.
It's supposed to be L in any arbitrary directions within x, y, z, which is fine. Okay, look, we can see cosine alpha is. It should be base over hypotenuse.
Yeah.
So L must be the hypotenuse. So
yeah.
Lz dot Z must be Lz, must be the magnitude of Lz. That's the definition.
Yeah.
So the drawing is incorrect. Okay. I mean, okay.
Yeah, drawing is stupid.
I don't know if it's incorrect. It's very confusing. So it's L.
No, it's incorrect.
L is being projected onto Z. That's Lz, and that's fine. Okay. And that's cosine alpha. So far, so good. Now he says that's now Lz dot Z. Well, we already said that Lz. We said Lz is MH, which is fine.
Yeah.
So we're still good. So MH over L. That's fine.
Geometry, the magnitude of the angular momentum vector can be written as the maximum value that Lz can take, from where we get the ratio between.
So this is. So I become confused with the max MH. What's the difference between MH and max MH? What is max MH? I never seen this max. No.
Max MH is, imagine that the angle the angle of the magnetic field would be the exact same as the angle of L.
So max
That's the max
max
MH.
MH is L. Is the magnitude of L. That is
Yeah.
the actual angular momentum.
Yes, but you have to understand that this LV is just a projection.
I understand, but like this max, like MH over max MH, I don't know what to do with that.
Yeah.
Anyway, and then he says, well, that's M over K. How is that M over K? Max MH is K?
Yeah.
I mean, that means max of M is K
Yeah.
from the previous slide. So the maximum M
Yeah. Exactly.
is K
Yeah, it's the maximum number that
because
them can reach is K.
because we said, if we go back, we said M goes from negative K to K, so max M is K.
Yeah, maximum is K. But I mean, it should be the module, the maximum module. I
Yeah, it's
think.
fine. Max is the
Anyway.
same. It's fine.
So
Okay, so that's just so cosine alpha is M over K. Let's see.
I mean, no, it should not be the maximum of the module.
Let me think about it. M over K.
Maybe. Okay. Okay. Yeah, that makes sense.
It's base. It's again base.
So
Base over
essentially,
base over
so
hypotenuse.
you can wait. You can interpret this as essentially the M is like the true orientation, and K is just the projected orientation.
No, K is
And when
the
the true orientation.
K is the actual. M is the projection.
No, it's the opposite.
M. Look at the colors. He has a color code. K is L. K is the
Yeah, and
original.
the M is the okay. So you're saying that M is the project. Oh yeah, M is the projection, right?
Yeah.
True. And K is the actual orientation. And the K is when the projection matches the exact orientation.
What?
So for K is when the projection matches the exact orientation.
No, K is in this case K is L. L is K. It's the same thing.
Yeah, K is L, but
K
is
but no,
L.
there's too many L's. There's L angular momentum and there is L, which is the modern K. It just happens to be whatever. Okay, it's M over K. Fine.
Okay, K is L, exactly. But
Look, this is like everything else was really simple, and this is really I don't have a good grasp of these equations. Like these last two lines, where he switches to max MH and then M over K, I'm fine.
okay, so this makes some sense.
Some
Like,
sense, yes, but
K
not
is,
perfect sense.
yeah, K is the K is the true orientation, right?
K's
So
L is the true
when you
orientation.
okay, K or L is the true orientation.
K is just a number. K is an integral.
Okay, so but K defines the actual orientation, so the angle.
K
in that
is
case,
an integer between negative.
okay, fine, but it's an integer that gives you the angle. So in that case, when you subject the thing to a certain magnetic momentum, you get the magnetic momentum of atom in relation to the orientation.
But this has nothing to do. M is the magnetic momentum. M is
magnetic number. M is the magnetic number. But when you get Yeah, it's the number for the magnetic momentum. So when you get like, so you get like the angle, and then you can have the you can have like the angle in relation to a magnetic field. And so when you pass the atom through a magnetic field, you can measure what you get in the M, and then you can figure out the K
Okay, this basically
in relation to
predicts.
that.
Wait, who came in?
So
Nobody came.
someone's in, someone's out.
I didn't know. Maybe Gamma
Okay,
left? I guess Gamma
so
left.
yeah, Gamma is out.
Look,
So
so right, this is going to end up as the Stern-Gerlach. This is where the prediction that it should go only up or down. This is basically it.
okay, so you get a magnetic field.
Basically,
measure
basically,
right?
basically, Sommerfeld said you can only
But you measure.
measure.
Wait. Okay, but wait. You get a magnetic field. You measure up, but you only measure like 1/2 of what you should measure.
What?
Right? You get a magnetic field. You measure up, but you only measure like 1/2 of what essentially you should measure.
I
That
don't
means that
understand what
K
you're
is somewhere
saying,
else.
and you're getting cut out. What are you saying?
Okay, so you put the atom through a magnetic field.
Yes.
You measure you measure M, but
No, you
it's
don't
like
measure. There's no measurement going on. You have a magnetic
okay,
field, and you're going to observe the atom. Right? This is we're heading towards Stern-Gerlach. So
you get a magnetic field.
Sommerfeld said, you take an atom, you put it, or a hydrogen, you put it in a magnetic, or a silver, you put it in a magnetic field B, it's either going to go up or down. This is where it's coming from.
But it will have a probability, right? That's the thing.
I don't think he believed in the. This is before Heisenberg's. So this is before
But I
Heisenberg.
think he was also thinking in probabilities as well.
No, there's no
I think
probability.
so. I think that.
No, there's a tendency. If it's going, no, there's no probability. If the atom is pointing up, it's going to fly all the way up. If it's pointing down, it's going to fly all the way down. That's it. There's no probability. If it's 50-50,
Yeah, but it
yes.
may or may not.
Yeah, if it's
Wait.
exactly horizontal, it's going to either go up or down. But what's incredible is that that means the magnetic field like is stronger. Like it has to do actually more work when the electron. Think of it. Let's say the electron almost points horizontally. So that's like then the magnetic field needs to do so much work. The magnetic field needs to do more work when the magnetic moment is horizontal, because theoretically it's not gonna. The electron is not gonna change direction. The electron is gonna keep the original direction. Theoretically, there's no time for the electron to change direction. So two electrons or two silver atoms, one pointing up and one pointing to the right. The one that's pointing perfectly to the right, the dot product is 0. So the B basically cannot have any effect on this silver atom. I mean, let's say there's an atom that is pointing perfectly to the right. How is B having any effect on it? And even if it's not perfectly to the right, B is going to have as much influence on it as it will on an atom that is perfectly pointing up. How could that be? Why wouldn't there be a linear some sort of relationship? So the answer is because it's multiples of H. Okay, but it could have 1H, 2H, 3H, 0H. So the answer is no. It's either 1 or negative 1. There's no 0. Nothing will be in the middle. So half of them will go up and half of them will go down. So either, and that makes sense because in the quantum world, there's only H. They only give each other H or AIDS. They only give each other H or 2H or 3H. In this case, they only give each other, the magnet only gives one H. But why does the magnet only give one H? Why? Why is their interaction limited? What's limiting the interaction? You have an atom. So, like you have two atoms, one pointing to the right, one pointing up. You're telling me that there's no distinction? The interaction with the magnetic field is going to be identical? Yeah? Because the interaction is not with the magnetic field. The interaction is with photons. Okay. So there's a photon, but there's many photons. So no, only one photon. What? How? How's this possible? There's many photons. There's many photons. There's many virtual particles running around. But this comes out of the least action or something. Who knows? I need to learn the least action. I think this comes out of the least action. So
Yeah, but with Sommerfeld, it's like what I'm thinking is like if you have a magnetic field that is like 45 degrees to the magnetic momentum of the electron, like how would that be?
I'll
Like
bet
it would have to orient itself to
no, it doesn't
that
orient itself.
magnetic field.
No, it doesn't
It
change.
has to.
No.
No, it definitely changes. But
From what I
if it's 90
understand,
degrees, like it would have a certain probability
no, it
of
doesn't. From what I understand, it
doing that.
doesn't change direction. As much as
Of course it does.
look,
Like, okay, come on. Like, that's the Aranov bomb experiment. It does change
I don't
direction,
know.
even when there is no measurable magnetic field.
They don't
It
talk
does
about it,
change direction.
but they don't talk about it. They say there's a force.
I don't care what they talk about or not. Like, it's an experimental result that's
No,
not
but I think
exactly
there's
debatable.
no. In order to reorient, you need two forces. It's like you need to pull it.
No,
Yes,
look, it's an
if there's
experimental effect that has been measured.
no, no,
Don't
no, no,
think
no.
about in order to. It's been
No,
done. It's been
no,
measured.
no.
Yeah.
Look, a magnet in a non-homogeneous field is not going to reorient itself.
Of course it is.
No, I don't think so. Let me show you. There's a video where they actually test it.
Okay.
Like the NSF made a video.
Hmm?
They reproduced Stern-Gerlach, the NSF, Stern-Gerlach old. Okay, stay on my stream. What? Go to hell. No? This is insane, insane, I tell to you. Okay, watch my stream. This is the NSF. So the NSF reproduced Stern-Gerlach. So this is the magnet.
If you're anything like me, your intuitive notions about magnetism are partly right and partly wrong, despite your experience with permanent magnets, soft iron, Canadian nickels, compasses. Probably never occurred to you that in the pre-atomic state, roughly half of the atoms in the periodic table are as magnetic as iron. These atoms are small permanent magnets.
Oh, I understood it right
As
now.
a piece of alnico.
Like, wait. Stop the video a bit.
Mm-hmm.
Stop the video.
I stopped a long time ago. Yeah.
Okay, but I have delay. I
Yeah.
understand where the p and the orbitals come from.
Okay.
Like, according to Sommerfeld, what would happen is that you'd have like that precession effect, and that precession effect is what dictates the shape of the p orbitals and the d orbitals and all of that. So that's where the L/K number comes from. And that's also, you can also see where the M number comes from, because it determines in which way it will process
But
in relation to the magnetic field.
ask
Yeah,
ChatGPT.
that's how it works
Ask
in this
ChatGPT.
model.
Ask ChatGPT. I think you're wrong.
Yeah, I asked ChatGPT, and as I was reading, I understood it, and then I asked ChatGPT to confirm, and it did confirm that exactly. So that's what I've been doing. If you, I'll give you the text if you want.
Let me just a second. Let me watch the video because
Using this apparatus, we'll demonstrate the magnetism of
I'll
individual
just
atoms,
copy paste
directing
it
them with magnetic forces.
really fast. Can I put it in the side chat or
Yeah.
in the other side?
you're a
But
mod.
more than that, you'll see perhaps you already
gonna
know
be big.
that magnetic atoms can't just
It's
have any
fine.
orientation in the magnetic field.
Gonna,
An effect
yeah,
that can only
doesn't
be
even
explained by
like
quantity.
me.
An experiment similar to the one you see here was first done in 1922 by Professor Otto Stamp and Walter Gerlach. Their experiment was with
We'll
atoms
read
of
it
silver.
later.
We use atoms of cesium
Let's
instead,
go to the
even though
video.
cesium metal in its condensed state, and here's an ampule of it, is just as lifeless magnetically as most things. But before we get on to atomic cesium, let's get straight to the basic question of the magnetic forces involved. What do magnetic dipoles do in magnetic fields? A compass is just a magnetic dipole that points north. So, to be sure, it always ends up that way, but if it isn't that way initially, it oscillates about the field direction for a while before friction brings it to rest. If atoms behave just like compass needles, then isolated atoms in vacuum, free of all friction, would oscillate about the field direction forever. In our experiment, we're not concerned with the oscillations, but with the net force on a magnetic dipole. Now, there are two orientations of special interest that we'll look at. We call them parallel or anti-parallel to the field. Here's a pair of Helmholtz coils with some iron filings. With current in both coils, we get a uniform field, smack in the center. When we put a magnet in the center, it oscillates about the field, but there's no net deflection in any direction. See? Now let's switch it off, on, off, on, off, on. So now we carefully set the magnet anti-parallel to the field in the direction unstable against rotation. This is the unnatural position. Our intuitions are sort of against it. To be sure, if it gets off its unstable equilibrium the least bit, it'll swing around. So I have to get it just right. It still doesn't tend to translate in the field. Off, on, off. In a uniform field, there's no net force on the magnet. Now let's see what happens in a non-uniform field. We'll put current in only one coil. You can see here the field is non-uniform. It's strongest where the field lines are crowded together. We put the magnet back in the stable position, and it tends to move toward the coil with the current in it. Off, on. It moves into strong magnetic field. Off, on, off. Now put the magnet back into the unstable position. It's a non-uniform field, of course. Anti-parallel. It's not so easy. Just there. On. There it goes. It moves into weak field, see? Off,
But will it rotate?
on, off. In a non-uniform field, then, there is a net force on the magnet, which depends upon the way it is oriented. Now, how big is this force? You know how to calculate it. Thinking of the small magnet as having equal but opposite poles at its ends. Then the net force is just the pole strength times the difference of field at the ends. But if the magnet lies along the field direction parallel or anti-parallel, the difference of field is just the field gradient times the length of the magnet. Calling the field direction
Is there
G, we
anything
can say that the
relevant
force.
What?
more in this video? Is
What?
there anything else relevant in this video?
I want to see how a normal magnet behaves because I don't even think it's going to. There's a torque. I don't think there's a torque
Yeah,
on it.
well, this is stupid. This is like like you have attrition forces, you have all sorts of things like that which you don't have on electron spins, and it's not quantized. Like it's
But if
completely
there's
irrelevant.
no torque, then it doesn't.
Completely different, completely irrelevant. I don't know what to say about this.
Wait, let.
Like,
Uh,
look.
I'm
The
only gonna
atoms
watch. I only want to
will.
watch. I only want to watch like the games he plays between the magnet. He's almost done. Let's see what he says. He's almost done.
Okay, fine.
F is equal to the dipole moment mu times the magnetic field gradient, dB by dC.
This is F. There's no torque for now.
To get a strong non-uniform field, we can use an electromagnet with special soft iron pole pieces with a cross-section like these. This powder pattern shows the kind of field you should get. Here is the iron, and here is the space between. It's strongest, the field is strongest, near the convex pole piece. If a small bar magnet is placed in the parallel orientation, it feels a strong net force pulling it toward the region of stronger field. It tends to fall into strong field. Whereas in the anti-parallel case, there's a repulsion on the side where the force is larger, so it tends to move into weak field. And so if atoms with magnetic dipole moments enter a non-uniform field like this, they'll be pushed one way or the other according to their orientation. Now, in the experiment itself, we can't just place atoms between the poles of a magnet and measure the forces on them. Instead, we send a stream of atoms between the poles in a direction perpendicular to the field, like this, and observe their transverse deflections. Here's a schematic of the apparatus. Atoms emerge through a narrow slit in a small container, which we call an oven.
But he didn't discuss if there's any torque.
A fraction of them get through a narrow collimating slit. As they pass through the magnet, their directions of motion are slightly changed by the magnetic forces. And at the other end of the apparatus, there's a small detector, which can be moved transversely to explore the deflections caused by the magnet. We also have a shutter in front of the oven that can block the whole beam before it enters the magnet. And between the magnet and the detector, we have an adjustable shutter. Of course, the apparatus must be in a good vacuum, so that atoms can travel from source to detector with negligible risk of collision. Now let's look at the parts of the apparatus.
Okay, so in this case, he did not discuss. He didn't discuss it.
Okay, so here's the deal. There's a few problems with this. First of all,
It's
like,
difficult. It's difficult to understand. The words are all
no,
cut
first
up.
of all, wait.
Hmm.
There are a few are you still watching?
Yeah, I'm with you. You can come. Yeah, I'm watching.
Oh, you
No,
still
I'm with
watching? I
you.
thought you had stopped the video.
I stopped. I'm
Oh, you're with
I'm
me.
watching you. I mean, I'm gonna copy your text because I can't
Oh,
see
okay.
it.
Fine. Okay, there are quite a few problems with this. The first problem is this assumes that the electron spin won't change near the magnetic field, which has been disproven. Yes, the electron spin will change in a uniform magnetic field. It will even change in a magnetic field that can't be measured. So just the how do you call it? What's the name of the thing? Like the A vector, like the how do you
Wait, do you
call
do you
it?
want me
How
to
do you call that?
do you want
I
me
don't know.
do you want me to read the ChatGPT what you wrote?
No, wait. Let's first discuss this, and then you'll read it later. How do you call like the spin of a magnetic field? How do you
Angular
call like
moment,
the
magnetic
angular
moment,
part?
angular momentum,
No, that's not it. That's not it. It is like
angular velocity, omega.
no. Oh my god. Fucking
Moment of
ChatGPT doesn't
inertia.
know what. Wait. Yeah, it's represented by A. I'm forgetting the name.
There's no A.
Yeah, it's represented by A.
A is
Oh
the
my
area.
god. That's not the area. It's like the it's like the spin of a magnetic field. Like you can represent the magnetic field. You can represent the magnetic field by its spin. And the experiment that used to be like a theoretical concept, and the experiment that proved that it's not just a theoretical concept. Yeah, it's called. They call it an electromagnetic potential, but it's not a good name in Wikipedia. But it's like the spin. Like you imagine that a magnet has like a spin, and the north is up, and and when the spin is up, it will point to the north, right? Like a spin, like an angular momentum. Yeah, there's a quantity like that used to be like considered to be just a theoretical, like something for theoretical analysis, but they call it electromagnetic for potential.
Okay, I don't know. Anyway, I'm falling asleep.
And
What?
yeah, but let me finish the explanation.
But you're putting me to sleep. I don't know what you're saying. I don't know what you're trying to say.
Okay, fine. Just try to pay attention then.
I'm
It's like
trying. You're
this.
putting me to sleep. I'm sleeping.
So
You made me sleep.
okay, fine. Just try to pay attention. Try
I'm
to not
trying,
sleep.
doing my best.
Damn.
Yeah.
It's like this. So the Aronov bomb experiment proved that even without a magnetic field, without a measurable magnetic field, but if you just the effect of that spin of a magnetic field changes the electron spin.
I don't
That's a
understand what you're
problem.
saying.
So that's a problem because now the magnetic momentum of the electron will change immediately.
I don't understand.
Yeah. So you got
Look,
that
I
problem,
told you.
and that's
Okay,
the problem.
let's ask ChatGPT. Does the silver atom change orientation? From what I understand, it
It
doesn't.
has to change orientation. Like that's what I'm trying to explain
Let's
to you.
ask.
That
Okay.
an
Let me.
experiment
Okay. Let me ask. In the
yeah,
Stern, hold on. In the Stern-Gerlach
whatever ChatGPT says,
experiment,
it's proven.
does the atom or change orientation?
Must.
Yes. The atom's magnetic moment related to its spin aligns with the non-uniform. Okay. Let me see. Aligns with the non-uniform magnetic field, causing it to experience a force in a particular direction based on its spin state. However, the atom's intrinsic spin orientation up or down along the magnetic field gradient is not changed by the magnetic field in a classical sense. Instead, quantum mechanics tells us that
Yeah,
the
that's wrong.
measurement process causes the atom to be projected into one of the possible spin eigenstates along the direction of the magnetic field gradient. Here's what happens in more detail. Initial state: when the atom enters the Stern-Gerlach apparatus, their spins are typically in a superposition of up and down states. Oh my god, the nonsense with the superposition along the axis of the magnetic field gradient. Let's call this the z-axis. Okay, it's in a superposition, meaning we don't know. It's in any whichever direction. Magnetic field interaction. The non-uniform magnetic field exerts a force on the magnetic moment of the atom. The direction, magnetic, and magnitude of this force depend on the component of the atom's magnetic moment along the z-axis. So the force is different, and we expect a distribution, a linear distribution. Measurement,
No,
quantum
we don't
projection.
expect a linear
Wait one
distribution.
second.
That's the problem.
Okay, hold on. Quantum measurement, quantum projection. Upon passing through the magnetic field gradient, the atom's spin state collapses into one of the two eigenstates along the z-axis, spin up or down. This collapse does not involve a gradual rotation of the spin, but rather an instantaneous quantum measurement effect. The atom is now in a defined spin state along. This is the most nonsensical explanation. And the AI is thinking in their terms of the nonsense, the collapse of the wave function.
That last part is actually correct. Like the atom has to jump to another stable state. It has to do that. And that's what makes it move in a certain direction.
So
That's
are you
fine,
saying,
because it's a
hold on,
non-uniform magnetic
that
field.
let me show you how why that's impossible. So let's say
How is that impossible?
Hold on. So let's say the atom is pointing just a little bit off the Z. So you're saying it's going to align with the Z. So what you're saying is, hold on. So what you're saying is that the change in magnetic moment is any number. It's not a multiple of H.
No, the change is one number, but
No.
the previous state is any number.
Look, you can't. The change cannot be any number. The change has to be a multiple of H.
I mean, wait. You mean the change or
Yeah.
the
change.
the value after the change?
The change. The change
The
has
amount
to
of
be a
change.
multiple of H, no?
No, the value after the change needs to be a multiple.
Why? Why? Is it does it know? Does it know that we're gonna measure it? Wait, how does it know? How does it know?
Does it need to know?
How does
I
it
mean,
know?
no. You're right. So the change, I mean, the change could be
Any number. You're saying the change can be any value.
No, I'm not saying that. The change has to be a multiple of 8 in terms of the energy that it takes to change. That can be, but that's nothing special.
Okay, I don't care.
That's just the energy.
Okay. Do you feel you understand it?
Yeah, that's
Okay.
just the energy. Like,
Okay, let me read number 4. No change in intrinsic spin direction. The intrinsic spin direction of the atom doesn't change.
That's wrong.
Okay. Doesn't change due to the magnetic field. Instead, the magnetic field reveals the component of the spin in the direction of the field gradient by separating the atoms into distinct paths based on their spin state. To summarize, the magnetic field doesn't cause the spin orientation to rotate or change in a classical way. Instead, it causes a quantum measurement of the spin, which forces the atom into a specific spin state along the magnetic field. Okay, I have no idea what's going on. This is
Okay.
Look,
Okay, that part makes no sense.
ChatGPT talks the way they talk, so I can't understand it. He talks like them.
That part, that last part makes no sense. So
No, none of
they're
it.
basically saying that
None of it makes any
the
sense.
spin is changed and the spin is not changed. So
Okay, I don't know what's going on.
that doesn't make any sense.
Okay. Okay, I
They're
thought
basically saying in the first part that it's forced into a state, but it also doesn't change. So it's forced into a state.
no.
That's change.
No, there's two spins. There's the magnetic moment of the orbit, and there is the spin. There's the intrinsic spin, which I don't know where that's from. I don't know where they got this spin from. Because when I asked them, how do you know about the spin? They say, oh, the Stern-Gerlach. It's like the Stern-Gerlach is the source of all their information. They learned everything from Stern-Gerlach.
Okay, but that's a problem because this interpretation of the Stern-Gerlach that the spin doesn't change.
But how did Sommerfeld predict? And why did Stern-Gerlach keep saying Bohr? This is not Bohr. Bohr never said anything about the Z direction. Bohr had nothing to do with this. They should have said Sommerfeld. Why do they keep saying Bohr?
Okay, whatever, doesn't matter.
What do you mean? I don't understand. I don't understand what they understood. And they were so excited. Oh, we're going to figure it. And they knew exactly what he meant. How do they know exactly what he meant? I still don't know what he meant. Unless they knew.
No, I mean, this is not.
No,
This is just not good science.
No.
No, this has too many assumptions. Yes, too much modeling, too many assumptions.
I look. These guys, I'll tell you how they're different than us. They knew math like we would never know math. That's my intuition. Their math
I would never know
skills.
math. What? I can learn math. I can learn math if I want to.
Yeah.
Like, I have no problem.
Their math. No. You need to know. For example, we don't know the least action principle. Can you derive a Lagrangian?
I know the least action principle. Yes.
Can you derive Lagrangian?
Give me Give me a few hours, I'll figure. I mean, not even a few hours. Give me a few minutes, I'll figure it out. Not now. I want to go to sleep.
I want to go to sleep.
but-
Okay, I'm tired. This is murderous on my brain.
Yeah. So, but no, I have no problems learning math. It's just
No, but they knew
fun.
math. My intuition is they knew math really well, and I don't know math well. I need to improve my math
All right,
skills.
fine. You just need to train. Math is a matter of training. Anyways, look, the explanation that the spin doesn't change in the this I said the spin doesn't change in the classical sense. It is forced into another quantum state. Blah blah blah. Okay, fine. It's just that's just words. That's just words followed. So it changes. That's that's the only possible conclusion we can take from the experiment. That's the only possible conclusion to take from the Aronov bomb experiment, which is a very important experiment. Yeah, like what can I say? Are you even there?
I'm here, but on my
Yeah, okay, good.
phone I can't see the channels on my server. I don't know what happened. Okay, never mind. Look,
Whatever. Time to go to sleep.
yeah, I'm
And
tired.
you read the explanation in the chat. Hopefully you'll understand how Sommerfeld came to the p and d orbitals. Like he was basically like quantizing the angular momentum, then like the p and d orbitals would be like when you subject the atom to a magnetic field, it would process in a certain way. And yeah, basically he got those orbitals from the precession that it would take.
Okay, whatever. I'm dying.
Yeah. Okay, fine.
I thought it would be simpler, but it's
All right. So if you only have like one electron, you'd always process in some kind of circular orbit.
okay. I'm going to
Yeah.
sleep. I'm dying. You killed me. That's it. You finished me off.
It's kind of weird though. I
What?
still need to think a little bit about it. Oh, all right, let's go to sleep.
I need to sleep. Yeah, I need to sleep it off. I'll see you
All right,
tomorrow.
see ya.
Okay, bye. Okay. Bye everyone. Let me just change the name. The name is this video basically. What's the name of this video? We're trying to make sense of this guy. Okay. Electron spin, and this experiment okay. All right, everyone. See you next time. Bye.